we can start with the session. So please, Cesar, go ahead.
Yeah, just remember the speakers, you have 15 minutes for presentation, following by 5 minutes of questions. And from the audience, if you have a question, please send me a direct message using the chat. So please go ahead, Guillermo.
Okay, thank you very much. First of all, I will share the screen as well. Just let me know if it is working, please.
Yeah, it is working.
Okay, thank you. So first of all, I'm Guillermo Gonzalez. Today I'm here to present position controller for a flapper wing drone using ultra-wideband. This is a research project that I did at the MAP lab of the TU Delft Faculty of Aerospace. And my supervisors and colleagues were Maciej Karasek, Diana Olenik, and Guido de Korn. And first of all, I would also like to thank the IMAV and the organizers for the opportunity to share my research with all of you. Having said this, let's start. So first, the context of the assignment was that this project was meant to be a collaboration between the TU Delft Faculty of Aerospace and a startup called Flapper Drones, which is currently focusing on the research and development of flapping wing drones, as well as some potential commercial applications. Currently, they are working on an accurate indoor positioning system for automating flight routines in flapper drones. And the company so far had explored the possibility of integrating ultra-wideband as a positioning system. The assignment in general, the objective that we defined was to design a controller able to perform full autonomous flights of a flapping wing drone by using ultra-wideband technology as source for position feedback. And then the main research question that we proposed was how can the ultra-wideband technology be used to design a feasible and accurate position control system for a flapping wing drone. Then from this main question, we had 4 sub-questions, each of them addressing the main elements of a control loop. So essentially, what would be the mathematical model for our system, what kind of controller we will require, the measurement error that we can expect from ultra-wideband, which is the feedback in our control loop, and lastly, how should the output of the actuators be modified to get a more stable response? Since this involves automating flight routines in a flapping wing drone, there are many main challenges, which I guess most of you must be familiarized with them. For instance, that the aerodynamic models of flapping wing drones are typically too complex for a real flight implementation. We also have to deal with inaccuracies of positioning systems that are mostly due to noisy measurements. And of course, we have the physical limitations that are inherent to flapping wing drones, mostly in terms of power consumption, the payload, and also the mechanical vibrations. The previous development was basically 2 tools, which we had already available from the beginning. So first, there is a working prototype from Flapper Drones, which is basically called the Flapper, as I will refer to it from now on. And in order to get the controller, we would work with the open source software developed by Bitcraze for their most popular drone, which is the Crazyfly 2.1. So essentially what we did was to take the firmware for the Crazyfly and make the required adaptations so that it would work with the Flapper. If any of you have before worked with Bitcraze software, then you might be familiarized with this control loop, which is the default controller that you have. Essentially, this is a triple cascaded PID controller, where our outermost loop is in charge of position and velocity. Then we have an attitude controller, and the innermost loop is an attitude rate controller. The sensors were essentially 2. For one side, we have the ultra-wideband system, as I mentioned. This ultra-wideband was working with a TDOA algorithm for the position estimation. And together, we also had our IMU. And then we had the state estimator module, which is, of course, required to feedback the measurements to both the position, velocity loops, and also the attitude loop. And here we have an important difference because the original implementation for the Crazyfly, for the state estimator, uses extended Kalman filter, which is in charge of estimating the values of these 3 controllers. But then when we made the adaptation at the beginning for the Flapper, we would see that the extended Kalman filter would only work with the position and velocity, but that the attitude estimation, this one we would have to make it using a complementary filter. And then the problem here is that the complementary filter only relies on IMU data, so it's not taking into account the ultra-wideband system. And besides, there is no integration between the estimates that we were getting from the complementary filter to feed back the extended Kalman filter. So these were some problems that we had at the beginning. Then after this, our experimental setup was essentially to build the ultra-wideband grid, which consists of 8 anchors, and each of them were located at the corners of a room. The sensor, the ultra-wideband sensor that we use, you can see here, is the Decawave DWM1000. And all our flight experiments were carried out at the flight arena from the TU Delft Faculty of Aerospace. This flight arena has also integrated another positioning system, which is a high precision OptiTrack system. So basically we had 2 position systems available. The first one is the ultra-wideband, which is the one that is sending the measurements directly to the flapper to perform all the onboard estimation. And we also had the measurements from the OptiTrack. Here it's important to mention that there was no integration of the system to the flapper. It was only used to provide a reference to know how accurate the measurements were from the ultra-wideband when compared to the OptiTrack. Then we did our first trials, and here you can see, well, what were the behavior that we were getting for position in X, Y, and Z, the same for velocity, and the same for the attitude in pitch, roll, and yaw. So as I said at the beginning, because we were using this complementary filter instead of the fully integration of the extended Kalman filter, we had many of these errors. So for instance, this unsteady takeoff at the beginning that you can see, a lot of oscillations and overshoots. We had some high commanded velocities. And here you can see a constant pitch error, but then afterwards we determined that it was actually due to some errors in the trimming of the initial values. But well, anyway, this was what I'm trying to show here is that, of course, the initial performance was not the optimal. And how to improve the performance, we approached with 3 different ideas, which were to define an attitude velocity model to account for the drag compensation. Because as you can see here in our initial performance, the value that we get from the velocity never reaches the commanded desired value. And we determined that this was most likely due to a drag that was affecting the response. The second solution was to model a voltage-dependent variable-based thrust for the height control, and also to look to the ground effects that might be influencing the performance of the drone. So now let's see each of these solutions individually. For the case of the pitch and roll, well, for the case of the drag compensation, we did some pitch roll velocity experiments. So essentially, we will only give a step input in pitch and roll at a certain angle, and then we would like to see what was our transient response in the corresponding velocity. And then from here, we would eventually reach a steady state value. Then the idea was that from this velocity data, we could model it following an exponential regression model. So the typical form of this equation, as you know, is this one here. And then what you observe here is that in blue, we have the data, the raw data that we get for the transient response in velocity. Then we only take certain values for the regression, which are the ones in orange. And then with this information, we are able to apply the regression model to see how it approaches to the real data. This was only to corroborate that we could actually extrapolate the final steady state values using the initial data. But then, of course, at the end, we would use all of the data for the regression. This is just an example to show that the regression model and the actual data would match with a certain error. And then for each steady state velocity, we map it against the angles. And then we will see that the plots that we obtained were also possible to model them with an exponential regression model. And we do this 2 times, first with the flapper, but we also take some data from previous experiments done with the Delphi. The Delphi is essentially another kind of flapping wing drone, but with a smaller dimensions. The flapper is a bit bigger. The purpose of trying this with two different models was just to check that the regression model could be applied regardless of the drone that we were working on. And then the plots were for pitch and also for roll. And then later on with this, we could actually get some way to model feed forward value that could compensate the drag that we were observing in our transient response. Then secondly, for the voltage thrust model, the second approach was just to do some hovering experiments and keep the drone flying until we get out of battery. The battery ran out of voltage. And the purpose of this was to find the base thrust that was required for each to a certain value of the battery voltage. As most of you may know already, of course, when the voltage of the battery decreases, then the thrust base shall increase. So we have this kind of inverse proportion relationship. And then from here, we would implement this model of the voltage to the controller so that we would see a variable base thrust. And we implemented this with the P and PI controllers. And also we check it against a constant base thrust. So summarizing, we would do 4 kinds of experiments with P and PI controllers, and also with the constant base thrust, but also with our regression model for a variable base thrust. And then we would try it under 5 different linear motions, which are simply in X, Y, Z, and also in XZ, so climbing up, forward, and sideways, also climbing up. Here I just show you some of the plots we had, so for the sake of simplicity. What you can see is that indeed the PIs will, of course, get a better performance than just the P controllers. This happens whether the height of the drone is the same, it is constant, or whether we have a change in the height. The influence of the variable or constant base thrust was simply that the standard deviation would be lower. So that means that our response would be more consistent, even though the battery voltage would begin to drop. And thirdly, we analyzed the ground effects. Essentially, again, it was to perform some hovering experiments at different heights, to use a voltage thrust relationship from the previous experiment so that we could correct for the real thrust. And then we would retrieve a thrust ratio. So as you know, ground effects appear when the thrust ratio is higher or smaller than 1. When it is 1, it means that we are getting same thrust that we are applying. And this was the equation that we used to model the behavior. And at the end, we find out that the ground effects were really not significant when we were flying above 0.5 meters of height. From 0.5 meters below, the ratio would drop to 0.92. So that means that most probably when reaching heights below that, then we would have some influence of the ground effects. But in this case, the heights of less than 0.5 were only occurring when we were either taking off or landing, so they really didn't affect the full flight. Here, after we implemented these changes, well, here you can see a comparison of performance. Once we were able to integrate the full Kalman filter against when we were using the complementary filter, then yeah, indeed, all the standard errors that we get for X, Y, and Z are smaller with the Kalman filter than the ones that we had with the complementary. So in average, we had errors between 11 and 13 centimeters, and then with the Kalman filter, they dropped to around 8 and 9. Here you can have a more qualitative idea. So here was the flight. We're working only with the complementary filter. So you can see that it should land here at the intersection of the tapes. Sorry about that. And here it should, when we use the Kalman filter, it reaches more easily the intersection. So there we could demonstrate that indeed the count filter was giving a good performance. And then lastly, we perform a validation where we define two versions of the controller. So one with the modifications, that is the modified version, and a raw version that is without any of the solutions that I just mentioned. Then we would analyze the transient response to step inputs of different amplitudes. So step inputs were of value 1 and 2, and then we test them in X, Y, and Z. And then we would measure both the position and velocity. You can see that in all cases, the modified version, the one with the changes, yields a better performance than the one we had with the raw version. And basically here, you can also observe the plots. So indeed, during rise time, which is below 1 second, the error of the modified version, which is the blue one, is always smaller than the one from the raw version. And also another interesting thing to observe is that most peaks of the modified version are above around 0.4 meters, while the ones for the raw version, they always go beyond 0.6. So yeah, in essence, we were getting a better results with the modified version. Lastly, the conclusions that we had are that the mean absolute error decreased approximately 1.5 times when using the modified version. We observed that our attitude velocity model was valid not only for the flapper, but also for the Delphi. So this means that this exponential model that we apply can be used for different kinds of flapping wing drones, as long as there is experimental data available. Then the voltage dependent thrust yields some more consistent performance. This is something that we observe in the standard deviation error, which was always smaller when using the variable thrust than the one we obtained with the constant thrust. And lastly, that the ground effects do not have a big influence as long as the drone flies above 0.5 meters from the ground. And lastly, we identified that there might be 3 interesting topics for future work. So the first one is that the drag compensation I mentioned was only applied for the controller, but maybe it could also be included for the estimation procedure. And then for this, we could use the IMU data. A second thing is that maybe a more robust implementation of the ultra wideband can get a better accuracy. As I mentioned, we were working with the TDOA algorithm for the position estimation, but so far we find that there are now more robust and sophisticated algorithms that could be used. And lastly, that in this case, we were working with the IMU, but as you know, because of the mechanical vibrations, the IMU measurements tend to be noisy. So maybe if we incorporate other sensor sources that are unaffected by mechanical vibrations, we might get better results. Some examples of these sensors would be a magnetometer and barometer. And yeah, that would be it. Thank you. And if you have any question, please feel free to ask.
Thanks, Guillermo. Anyone have a question? I think we have time for 1 or 2 questions. Well, I have a question, Guillermo. In your first slides, when you show the diagram of your controller, your cascade PID controllers,
Sure.
I think altitude, yeah, they have different rate frequencies.
Yeah.
Could you explain the reason they have different frequencies?
Yeah, sure. So basically, for the attitude rate, we are working with a higher frequency because the accelerometers deliver measurements at a quite fast rate. So we need to get the data, sample the data faster. But then for the position and velocity, the dynamics of the system are slower. So yeah, there is a sampling frequency that is smaller. But in this case, the way we can compensate for it was just that we would average, let's say 5 samples, and then that average is the one that is sent to the position and velocity.
Okay, so you use average to synchronize the controllers, right?
Yeah, precisely.
Okay, thank you. Thank you, Guillermo. I think we are in time now. So paper number 23, I think is Joe, right?
Yeah, I'm.
Yeah.
Hi.
Hi,
So
Joe.
let me share my screen.
Yep. Please go ahead.
Okay, this should be visible, I think. Oh, is this the wrong screen? Wait a minute.
Don't worry.
So are you seeing the full screen of my PowerPoint presentation or the presenter view?
We are seeing now your onboard time optimal control for tiny quadcopters.
Yeah. Okay, perfect. All right, so let me start. I apologize in advance if I speak very fast because I have some trouble meeting the 15-minute requirement. So if it's something that is not clear, ask me the questions at the end. So hi everybody, my name is Jelle Westenberger and I will be presenting our work called Onboard Time Optimal Control for Tiny Quadcopters. This research was performed also at the IMAV lab in collaboration with Christophe de Wachte and Professor Guido de Kroon. And we propose a controller that is a lightweight model predictive controller that approximates some time optimal principles. So for those unfamiliar with optimal control, it is basically the field of mathematics where you try to find a series of control inputs that optimize a certain cost function with respect to some value. So you can, for instance, optimize for smoothness or for spent energy. But in our case, because we are focusing on drone racing, we are most interested in optimizing for minimum time. So in general, solving these problems is done by satisfying either the Hamilton-Jacobi-Bellman equation or satisfying the conditions for optimality, as stated by Pontryagins minimum principle. And there are generally numerical solvers like nonlinear programming or dynamic programming methods that solve these. But these are quite computationally expensive. So you have the choice to calculate your optimal trajectory beforehand, which has the disadvantage that you cannot incorporate any environmental changes on the go. Or the other choice is you calculate your trajectory on the go, and if you incorporate your quadcopter model, you look at model predictive control with the big advantage that this is very dynamic, so you can react to changing objects in the environment. But the downside is that you need quite a powerful computational module to be able to do this. A more recent approach that has been done in research is using machine learning to, for instance, train neural networks to approximate some reference trajectories that are calculated by the traditional methods, and then execute these on the fly. The downside of this method is that it's very data intensive and time consuming to train these neural networks. So summarizing some downsides of the current method is that it's too computational expensive to easily implement it on board a quadcopter. In terms of machine learning, it is often too data intensive to quickly implement it. And there are a few efficient trajectory generation methods that can be executed on board. For instance, the minimum snap trajectory generation by Mellinger and Kumar is one of the most popular papers in this field. But just like this example, it is not time optimal, but it is actually optimizing for a certain smoothness of the trajectory. So here comes our proposed controller, which we call the bang-bang controller. We call this the bang controller because it is based on the assumption that for constrained time optimal problems, the solution often has a bang-bang shape. This means that the input values are either maximum, 0, or minimum. And the big advantage of assuming this is that the control problem only reduces to a problem where you only need to find these timestamps at which it will switch. So you don't need to worry about the values of the control inputs anymore. So our approach is to plan a bang-bang maneuver between two targets and then optimize the time at which you switch from accelerating to braking based on path predictions. So we try to reach the target with a certain desired velocity, and the switching time is optimized until the velocity error at this target is small. So the attitude angles, pitch or roll, are always saturated, but only one of the two, because if we want to extend this problem to two directions, we have to look at what we call a critical direction and a non-critical direction. And what this is can be shown in this example. So here we say that this longitudinal direction is the critical direction. So we plan a bang-bang motion in this direction, which is in this case performed by planning bang-bang in the pitch angle. And we have a so-called minimum effort angle in a non-critical direction, which is the roll in this example. That is where we calculate a constant angle value, so such that this position is reached at the same time as the longitudinal component of the position. So you don't waste any power on the lateral. You don't waste more power than needed on the lateral direction, while you maximize the power needed for the critical direction. So the control parameters in this problem are the switching time and the non-critical angle, and we calculate this based on path predictions. So as computational efficiency is our main node to take away, we need to look at a simple path prediction formulation, which should be analytically an analytical model. So we find this by reducing the dynamical model of the quadcopter quite a bit. So we assume linear drag, we assume constant thrust and therefore also constant altitude. And of course, the attitude angles are assumed to be constant during the path prediction. Summarizing, we can derive some differential equations, which calculate the position and speed at any time. And by combining this, we can use a bisection scheme to iteratively optimize the switching time or the non-critical angle. So when we start in the critical direction, we have here a path prediction, which consists of a acceleration phase and a braking phase. And we assume that during this each phase, the attitude is constant and also that the thrust is constant. And during the transition, we assume that the angle, for instance, the pitch angle, changes instantaneously. Then we use a simple bisection scheme that starts with an initial guess of switching time that iterates on the switching time until your velocity error at the target is within a certain precision. When we have a nice value, then we start with the non-critical direction, and this uses the same bisection scheme, but instead of switching time, we now change the roll angle, or the non-critical angle, I should say, such that the lateral or the non-critical position error is minimized at the same time as the estimated time of arrival that we have gotten from the first optimization loop. And finally, also while we're braking, we also optimize the angle with which we are braking to incorporate any premature braking because of imprecisions. So when we summarize the computational effort that needs to be done for this optimization loop, we can say that for the switch time, we only need 4 function evaluations of these 2 functions per iteration. And on average, we need about 10 iterations to reach a certain desired precision of the switching time. Same goes for the non-critical angle, but then we only need 2 function evaluation. And if you sum this, then we can say that during the acceleration phase, we only need 60 total evaluations to reach a desired switching time and non-critical angle. And during the braking phase, only 40, which is not a lot at all. So we can say it's fast enough for a real-time model predictive controller that can run on board a quadcopter. This we first tested in simulation. We compare our method to some reference trajectories done by that look like a minimum time trajectory, and also by a more traditional high gain PID controller. So the minimum time trajectory is calculated with the popular iClocks toolbox, which uses direct collocation to calculate this trajectory. We performed some simulations, first in a straight flight. Here the blue line is the minimum time solution. You can clearly see there's a change in altitude as well. And the purple line, I hope it's visible on screen, it is straight because we assume constant altitude. And despite it being very fast, it also shows some overshoot at the target. Similarly, in a cornet flight, it overshoots its first target and also overshoots its final target. So we need to worry about why this is happening. In order to identify this, we look at the prediction accuracy. So, and for that, we can look at our estimated time of arrival during simulation. Because if you have perfect prediction from the start, you can assume that the estimated time of arrival should remain constant. But as you can see in these plots, they actually increase during the rotations. And this makes sense because we assumed instantaneous rotation switches. So at the switching time, it would switch from the braking or acceleration angle to the braking angle immediately. But in reality, it will of course cost a little time or take some time for the drone to rotate. So in essence, we will always brake too late, and we need to compensate for this somehow. How we do that, I will explain in a few slides. Because first, we have performed some flight experiments at the same lab that Guillermo also did this experiment from the previous presentation, which is the Cybersu. Our drone that we use is the consumer-grade quadcopter called Parrot Bebop, and it has been modified to run the custom Paparazzi UAV autopilot software. So here's a brief overview of our control pipeline. In addition to the optical tracking system of our lab, we also use a complementary filter to improve our position and velocity estimations. Then we have a PID controller for the altitude control, our bang controller, of course, and a high gain PID controller that takes a more traditional approach to control. The bang controller and the PID controller spit out create roll and pitch commands, and these are given to the inner loops, which are based on INDI. So here's an example of what happens during a maneuver. On the left plot, you see the prediction of the critical direction, where the blue line is the actually flown path and the green line is the acceleration prediction and red is the braking prediction. The right plot shows the non-critical direction prediction. And yeah, in a perfect case, the roll command should remain constant, but because of inaccuracies, we can see that it will change more quickly as we get closer to our target. So as I mentioned before, we need to compensate for our transition losses. So for the fact that it takes some time to rotate from one angle to the other. Also with taking computational efficiency in mind, we know that it is difficult to model. So we have defined some rotation losses, which is the time it takes to rotate from one angle to the other, and also the position and speed that we lose during this rotation. If we can approximate this somehow and augment our path prediction with these values, we can hopefully convert to a better switching time. So we approximate these losses with a simple linear regression model. We obtained this model by simply measuring our time, speed, and velocity in flight during the rotation. And then we have created 3 models for the forward, backward, and sideways motions, because the quadcopter is not aerodynamically identical in these directions. So here are some, we have performed some experiments where we start from rest and end in rest, and tested in the combination of longitudinal and lateral flights. We compare our bang controller to the bang controller with the compensation system enabled, and also we compare to a traditional high gain PID controller. So in this video, we compare the bang controllers with compensation and without compensation. These videos are overlaid on top of each other. The green drone has compensation enabled and the red one hasn't. And you can clearly see that in both cases there is some overshoot still, but the compensation system is definitely doing some good in terms of overshoot. Similarly, if we compare the bang controller without compensation to a PID controller, we see quite some overshoot for the bang controller, and the PID controller barely has any overshoot. This is better visibly in these box plots. These are box plots of each maneuver that we have performed. The BBC label stands for bang control with compensation enabled. And you can clearly see in each plot that shows the overshoot that it is much better than the bang without compensation. But it doesn't come close to it doesn't reach the same level of overshoot as the PID. And this is because the PID controller is in essence a controller that is either critically or even over-damped in position control, because it is proportional to your, because it will follow a desired speed, and that speed is proportional to your position error, and it has been tuned in such a way that it won't overshoot. But this also means that in theory, it should brake too early And that is the place and time where the bang controller should perform better than the PID controller if we managed to calculate the switching time more precisely. Also, because we designed this controller with drone racing in mind, we need to look at a scenario that more closely resembles drone racing. So we've come up with this experiment where we have 4 waypoints at which we don't intend to stop, but perform a continuous flight. We keep our heading constant because that's unfortunately one of the requirements of the bang controller. And we automatically switch the direction which we consider to be critical based on the largest position error. So this is a video where we can see what happens for both controllers. So the green one is bang with compensation, and the red one is the PID controller. We can see that both controllers manage to complete at least one circle, but the PID controller oscillates and also loses stability at the end. And this plot shows it more clearly. On the left the bang, on the right the PID, and we can see also when we look at the distance to each waypoint on the right plot here that the bang controller flies through the waypoints much more closely than the PID controller. And we can see that the PID controller will overshoot its first target and then also start to oscillate in order to compensate for this overshoot, which ends up that the PID controller is less stable than the bang controller, but also it takes longer to complete a circle. So the bang controller is here about a second faster on average. So the reason that this happens, or that we see this difference in behavior, is because the bang controller is able to prioritize thrust to one direction. Because we have bang maneuver in one direction and a minimum effort approach in the lateral direction, while the PID controller uses the same gain values for both pitch and roll. And if we this equation basically approximates how much thrust we need during the flight. And if both pitch and roll are high values, these terms become very small, so the required thrust is much higher. This means, this we can also see in this video. The red one is the PID, and you can see that right at the start of this maneuver that the PID controller moves to the right immediately, even though its largest position error is in the longitudinal direction. And the bang controller flies more in a straight line to its intended target, which is more power efficient and makes it more stable. So the PID controller is always closer to its maximum thrust capability, therefore less stable, and therefore also slower than our proposed controller. So this brings me to our conclusion. We have proposed a lightweight bang model predictive controller, which unfortunately still comes short in step responses, but in theory should beat the PID controller in the braking phase. It outperforms the PID controller in continuous flight because it can give different priorities to different axes. And also it is about 7.5% faster on average in completing circles. It is easy to implement because we require only minimal knowledge of the quadcopters dynamics. We only need mass and drag, and we need to estimate transition losses. Also because it's very computational efficient, it can be implemented on many drones, also with more limited computational resources than the Bebop. On the Bebop, it was able to run at 512 Hz without even saturating the processor unit. And compared to the PID controller, it has the advantage that we don't need any gain tuning or gain scheduling. It can fly many different maneuvers from the go without any tuning. And under some strict conditions, we can say that we approximate time optimality under the conditions that our angles remain constant, such as the heading and the pitch and roll during the acceleration phase. Also, we need to assume constant thrust, so we cannot incorporate any maneuvers that require a difference in altitude. And finally, one downside is that we need to predefine the desired velocity at the targets, which means that our solution is not globally time optimal for the entire trajectory. So finally, my future recommendations. We have set our pitch, roll, and thrust limits conservatively. In future work, this should be made adaptive so we can fly close to the limit of the quadcopter. We can explore a different way of calculating bang maneuvers. So instead of roll and pitch, we can look at the thrust factor and point it towards our target or away from the target, and then translate that back to roll and pitch angles. Yeah, as I mentioned before, we had to do some effort or make some effort to estimate our transition losses, but this can also be done online, for instance, with recursive least squares method. And finally, we have praised our computational efficiency, but not actually analyze it in a proper way. So we need to analyze, for instance, how much floating point operations we need in order to quantify our computational effort. Well, that brings me to the end. So if there are any questions, I'm happy to answer them.
Thank you, Joel. I don't know if someone had a question. We are in time now. Yes, I have a question. How do you ensure that you have the best PID gain selection?
Yeah, well, we used one set of gains for the PID controller to keep the comparison fair, and we tuned these for the maneuver where we have a longitudinal and a lateral offset. So yeah, it has been tuned by by only looking at the maneuver where we fly forward and straight at the forward and laterally at the same time. And that has been tuned by trial and error, basically, so that we can get the best performance for that maneuver, and then we use the same values for each other maneuver as well.
Okay, thank you. And finally, one final question. Have you compared your approach with a nonlinear controller, for example, saturated PID?
No, I'm afraid not. We only compared it to the theoretical time optimal solution and the high gain PID controller that I mentioned before.
Okay, thank you for your presentation, Joel. I think Romain, are you ready?
Yes, I am ready. Good morning, everybody. Can you hear me?
Yeah, we can hear you.
Okay.
Please go ahead.
I can share my screen. Can everybody see my screen?
Yeah, we are able to see the screen.
Okay. Sorry. So good morning and good night to everybody. I'm Romain Jean, a PhD student in ISA Super in France in aerodynamic department, and my co-director of thesis is Dr. Jean-Philippe Contamine from ENAC, and my director is Professor Jean-Marc Mosqueta from ISA Super as well. So I'm about to present you the modification I've made on a fast simulation model for control law design and benchmark of high aspect ratio UAVs. So during my work, I'm using the software called AI Swing developed by Professor Magdalena at MIT during the 80s. And it's mainly used to simulate the behavior of flexible aircraft, but specifically high aspect ratio aircraft. And it used many different theoretical results that we have decided to study at ISA Super. And we have chose this software because of the different function it proposed, such as modal analysis, frequency analysis, and specifically temporal simulations. As it uses different theoretical backgrounds, it kind of imposed a workspace that I just recalled here on the right. So we have to use high aspect ratio wings, and it allows small to high deflection regarding the flexibility. And you can study aircraft until Mach 0.7 that because it uses compressibility transform space to recover an incompressible space. You can simulate up to 20 beams, 20 different beams, so that you can consider as lifting surface. And you can also implement up to 12 engines, 20 flaps, and you can put as well 20 sensors that can monitor up to 40 different physical variables. Just to give you an overview of, for example, the aerodynamic loads computation under iSwing and the different theoretical background used. It uses an unsteady lifting line theory using the vector form of unsteady Kutav-Joukowski theorem. And it uses also the influence function of different objects on the aircraft, such as vortices and volume influence, as well as jet swirl, which is very interesting for investigating the effect of the propellers over fuselage or wings. And separation and stall are modeled to predict lift and drag up to pre-stall, and we do not recommend post-stall behavior study. And regarding drag, it uses three-component: friction, pressure drag, and a post-stall contribution. Regarding fuselage, it uses an unsteady form of the slender body theory that I would not recall here because it's a bit out of the scope of this presentation. Just to give you a motivating example, we are looking at ISAE Super-Héros to show that I-swing is still accurate for modern application. So I'm just giving you some simulation we have made regarding experimental data for tandem aircraft, which are a bit studied today, especially in China, for example. And we have managed to show that I-swing is accurate to predict lift and drag for a certain range of angle of attack. So I-swing is still accurate for modern application, but regarding the control part, you can only implement multi-input, multi-output PID controllers. So the idea was to modify I-swing so that you can implement a bunch of modern control law strategies. But as I-swing is not a MATLAB black box, but a compiled program, we had to look into the program because the source code is accessible, and modify it so that we can implement our control law strategies. So this scheme represents the actual or the current control law strategies that you could implement under I-swing. And basically Q and U are different state vector, and Q are the censored physical variable. So the problem statement is that we have to modify the solver, which is used for different type of simulations, such as modal analysis, frequency analysis, and temporal analysis. And it uses always the same strategy, which is a Newtonian descent multi-order algorithm. So I-swing is very efficient. I forgot to mention that because you can run simulation in almost real time, and it's efficient because of the way how the solver has been implemented. And so we have to respect a certain pattern so that the internal solver use very efficient matrix inversion algorithm to solve the temporal iteration very quickly. So the idea was to implement the control law that I have summarized here in a nonlinear form first, and then to invert the extended Jacobian matrices that you need for every problem, such as time marching or modal analysis. So first of all, the idea was to modify the source code to implement the nonlinear control law, but the main drawbacks was that every time you want to change a nonlinear control law, you have to go into the source code and compile again I-swing. So the idea was to propose a linear control pattern that kind of recover as much as possible the linear control strategies that are used nowadays, and use it as a black box with MATLAB. So you don't have to go into the source code anymore, and you just have to give the different matrices of each block that I will present. So the pattern is made of different blocks. So the first one was to add actuator dynamics because they are not simulated under I-swing, and the saturation blocks. as well. We did the same for sensors blocks, and we had controller block dynamic and also anti-wind up system for the people who wants to investigate stability problem for saturation problems. Note that every block can be scheduled by any variable from the Q vector, so up to 40 different variables. They are following a multivariable input-output linear pattern, and we have implemented, three different methods for addressing gains. So nearest neighbors and bilinear interpolation that was already used with the previous controller strategy in I-swing, and the bipolynomial strategies. So I just made a tab to kind of summarize the different linear controller strategies that you can implement as long as they are following a linear state vector form. So, and of course you can still implement linear controller strategy, but you will have to change and modify the source code, which is not very practical yet. Finally, I'm just gonna give you some quick example as illustration. So the first one is very easy. It's just to show the difference between the current controller strategies and the previous one, where we have implemented just first order dynamic for the engine with a 3-second time response, and we have set 2 different saturation levels for 0 thrust level and 7 Newton thrust, 7 Newton saturation level. And we can see that now the engines behave more like a real physical system. So that was the first example. Then just to show why we have decided to modify the internal controller strategies, just a simple example. The previous work has shown that it is possible to harvest energy and gain altitude with the adapted deflection of the elevator of any UAVs flying through a gust. And this example just shows the effect of an actuator dynamic on the closed loop system. Sorry. So we thought that it was more realistic to simulate the behavior of an aircraft with the actuator dynamic to see the real effect on controller strategy in closed loop. And the last example is just a motivation example for energy harvesting and the limits of basic controller strategies. So we have implemented a function on the I-swing that can simulate Van Kalmeren 3D spatiotemporal gust environment. And we have shown that for the same controller strategy where we were gaining altitude through time, here the objective of the controller strategy is not fulfilled anymore, and we have some kind of random behavior through the time, and so it motivates the needs of investigating new and modern controller strategy regarding energy harvesting. So those are just 3 examples to illustrate kind of the toolbox we propose here. So sorry, I have been a bit quick, so thank you very much for your attention, and I will answer your question.
Thank you, Romain, for your presentation. Anyone have a question? We have a question. So where is the simulation carried out? MATLAB on, and which is the numerical method used?
Sorry, can you just repeat?
Where is the simulation carried out? MATLAB, for a question. And which is the numerical method used?
For the simulation, we have used the software, so iSwing, but you can output the data and plot them on MATLAB. So it's a MATLAB plot, but this is the software simulation. And regarding the numerical method, is it regarding the solver or the overall theoretical background of iSwing?
Cesar, I think it's about they want to find out about the numerical method that you use in your work.
Yeah, the question, well, the person who made the question says, yes, for example, RK4.
Okay, so regarding the numerical methods, so a same solver is used for 3 different strategies. So modal analysis and frequency analysis, where you study the steady or unsteady Jacobian of the residual system of equations. And for time marching computation, you are using a Newton descent algorithm to reach the residual perturbed state residual equation to 0. So the overall problem is to study the Jacobian matrix and invert it. So the numerical methods, it's a Newton descent algorithm. And regarding the inversion of the matrix, it's used a Gaussian block matrix elimination algorithm. And inside this algorithm, you can identify different patterns that can solve the problem quickly. And specifically, this state vector, I won't explain you what those variables are, but this state vector, it's a differential equation, follow a specific pattern that you can use to really get the solver quicker.
Okay, thank you. Anyone another question? Okay, I think we have no more questions. So thank you, Romain.
Thank you very much.
We're just in time for the next session. The next session called applications. I don't know if presenters are already in the room. Paper number 4, paper number 13, and paper number 22. I saw paper number 4 and 22. Gauthier. Can you hear me?
Yes, we can.
Yes, I can unmute.
Okay. And paper number 13, I think it's not already on the room, right? Okay, so we have 2 minutes for the next presentation. I don't know if you have some announcements.
Just a reminder that we will have our second panel session of the conference, and that will happen after this session finishes. So yeah, don't miss that session. Thank you.
Okay, thank you, Jose. Okay, so we could start, Gauthier, with the first with your first presentation. Go ahead.
Okay, let me Can you see my screen?
Yes, we are able to see your screen.
Okay, so hello to everyone. My name is Gauthier Tonberger. I'm a researcher and assistant professor at INAC, the French Civil Aviation University. So my presentation today is a field report of a project aiming at deploying a fleet of drones for cloud exploration. And this project is called NEFELAE. This is actually an atmospheric science project. And the goal is to understand the evolution of the evolution of clouds during their lifetime. And to do that, we need to deploy several drones and to have adaptive exploration to be more efficient. And this was a collaboration between INAC, LAS CNRS, they are specialists in robotics, and the Météo France, the Research Center for Meteorology in France. The technical objectives of the project regarding the UAV side was to be able to track cumulus type clouds during their lifetime. And actually this life cycle is quite short, it's about 20 to 30 minutes. And because the winds can carry the clouds, we have to be able to track them up to 6 to 10 meters per second of average wind. Then we need to collect data, and the scientists are actually looking at very specific locations of the clouds. It's not a question of just going through it without really knowing where we are. They want to get especially data from the border, so the place where you have an exchange between the open air and the inner the inside of the clouds. And they are also interested with the center where you have the maximum intensity of the internal phenomenon. So to do that, we need to navigate using the sensor data in real time. And finally, we want to fly several UAVs at the same time in order to get synchronous data from different locations and especially from different altitudes in order to measure some airflow inside the clouds, which means that we need to coordinate the flights. So all the details of the trajectory that we have been using have already been published, and you can go through these previous publications. Yeah, so my presentation here is to is about the field campaign, because the NEFELAE started in 2017, and the end goal is to actually deploy in a real life mission. And we had several preparation flights, especially in France, in a place called Lannemezan. And it's very difficult to deploy the complete system and test the sensors in real conditions, just because it's difficult to get flight authorizations to go high enough. So let's say 1,500 meters at least to get the clouds. It's not possible to get a large flight area, so we can follow them for a long time. And everything is quite difficult to test beforehand, but we had these opportunities to test some parts of the systems. And also finding the correct locations to perform the real scientific flight campaign is also difficult. And several places have been tried or envisioned to do that. And finally, we had the opportunity to join an international meteorological campaign that held on the Barbados Islands end of January 2020. So just before lockdown, we have been really lucky to join this campaign that involves piloted aircrafts, drones, boats, unmanned boats as well, and so on. So after this introduction, I will present the preparation and logistics to do this Barbados mission, and then the field campaign itself. Okay, the first thing to prepare the mission was to find the correct locations on the island where to fly. It's a rather small island, and there is at the south international airport. So we have to find a place which is far enough from the airport so that we don't intersect the aircrafts during their initial and final approach. And also we know that there is this cloud observatory here on the islands. That's the only possible place where we have enough space and far enough from the airport is at the north of the island here at Morgan Lewis, which is this place here with a large field where we can operate. And it's directly in front of the sea. So actually the wind is coming from the oceans, pushing the clouds towards the island. And the general flight plan idea was to fly within this triangular shape, which is around 14 kilometers long. So fly to the end of the flight zone, wait there to get some, to find some clouds to follow, and come back with them towards the island. And the flight ceiling was between 1,000 and 2,000 meters above sea level, depending on the flight authorizations. In terms of logistics, we had at least 10 people involved during this mission with researchers, engineers, and PhD students. It lasted for 4 weeks, not all the people together at the same time, but still a lot of people to manage. And also we had to send all the equipments, which, planes, ground equipments, laptops, tools, batteries, at least 2 months in advance with a cargo ship. And it was actually even quite difficult to get them out of customs. And for the operating center, we had 3 containers for storage and operations. Now the deployment strategy, we had assigned 5 roles to the people. So the first one is the atmospheric scientist. His role is to provide the high mission goals. So what are we looking for? And also to look at the real-time data coming from the planes to assess their quality and to tell if the signal is an actual cloud and if it is worthy to start the tracking of the cloud. The second person is the map maker. So is a computer scientist here in the middle, is monitoring the real-time cartography system. So based on the data measured in real time by the planes, we are constructing a map of the clouds on the ground, and we are using this to monitor the system and also to give some information to the aircraft to improve their autonomous navigation. The next operator is the UAV operator itself. So here on the right, his goal is to monitor the flights of the UAVs, mostly for the safety of the operations, of course, during the takeoff and landing, reaching the end of the flight zone. And when the tracking starts, he gives the control to the atmospheric scientist and map maker to do the automatic tracking. Then we have the safety pilot outside handling the critical phases of landing and takeoff, and we have only one for all the aircraft flying at given moments. And finally, we have a flight director, which is doing the general coordination between all the other operators, but also with the other teams operating on the zone, because we were 3 teams operating drones from the same fields, and also be in contact with the air traffic controllers of the Barbade. And on the right here, you can see the general software architecture of the system with the autopilots. So everything is handled on board by the autopilots. The second processor is only for getting the data and sending it to the autopilot, which is doing the automatic adaptive navigation. and stabilization, communication, etc. And on the ground, you have here the UAV operator and the atmospheric scientist and map maker looking at the mapping system. So the airframe that we have been using are commercial foam aircraft, X6 Skywalker, about 2 kilograms, 1 hour of flights, takeoff from the Benji. The main reason to use those type of aircraft is that they are very robust and easy to repair. During the project, we have been developing custom design aircraft with tremendous characteristics, like more than 2 hours of flights and very fast flying. But it was way too fragile to be used in actual real flight campaign. And yeah, one of the important things that we have learned is that we should prefer the robustness and ease of repair when in the choice of UAV. The most important sensor for the navigation is that we call the cloud sensor. It's actually LEDs emitting lights that are what to say? Sorry, that are monitored by this small sensor here, and it's measuring the retrodiffusion of particles of the atmosphere, and it's able to tell first if we are inside or outside the cloud, and also to reconstruct some physical characteristics of the atmosphere. And of course, we have long-range modems and the paparazzi UAV systems to fly the planes. So the general flight plans operation, it's a 5-step classical takeoff, then going to the initial climb to reach the target altitude. We know from the ground observations the roof altitude of the cloud base, so we have to be slightly above that. Then we reach the end of the flight zone, and when we had the chance to find clouds with the cloud sensor, we start the tracking, and this strange shape here is the automatic adaptive tracking of the clouds until we reach the end of the flight zone or the coast, and then we have the landing. So to summarize the flights, we had up to 48 flights, 22 with 2 UAVs at the same time. Lots of hours of data recorded. And among the flights, we have 23 only for calibration and validation of the flight pattern strategy and sensor calibration as well. And so 25 for measurement flights, and only 18 finally that have been able to track the clouds for at least 2 minutes. And yeah, and not so many crashes. We have only lost 1 plane, or actually we have broken 1 plane beyond repair. Okay, so what have we learned from this flight campaign? The first thing is that operating in a foreign country, it makes every little thing a little bit more difficult or way too difficult. If you cannot afford to forget anything from your lab, because you will not find locally and in a short time. We have spent a lot of time to do calibration flights, and one of the reasons is because flight testing is really difficult. Flying inside the clouds and following them needs a very large airspace, and it's very difficult whenever you are. Also, the initial plan was to fly up to 5 UAVs, but we have been only able to fly 2 at the same time, or actually we have intended a flight with 3, but one of the plane had to land shortly after takeoff for technical issues. And that's one of the reasons, the number of available sensors, planes, hardware failures that we couldn't repair during the mission. And also the operator and safety pilot workload, because there were only one safety pilot and one operator. It becomes exponential when you increase the number of UAVs. And important points, searching for clouds with only local perception is really inefficient, and we need to get better systems to guide the aircraft to the initial points to find the clouds. And when we lose a cloud, we also need a better recovery mechanisms to get back to the tracking. So the future improvements, the first one is to, as I said, improve the robustness of the adaptive flight patterns, especially with a recovery mechanism. And these have been implemented and tested successfully in France, but with only hybrid simulations, which means that we have a real aircraft flying, but simulated clouds, and the flight altitude can be very low and close to the ground. The second point is that we should use vision-based systems to detect the clouds. Metro France is working on a camera system called All Sky, a network of camera actually to try to measure the initial position of the cloud, and we have to feed that to the system to find the cloud faster, and don't lose time waiting for them. And finally, we have to integrate a task planning and collision avoidance system so that we can lower the UAV operator workload. And this is also ongoing work at LAS. So as a conclusion, I would say that atmospheric science is a very exciting field for a UAV system. It deals with very complex and unknown dynamic environments, and UAVs are very good at that, and they are good assets, but we still need a lot of works to make it very more practical to use and to deploy, especially as a fleet. It stays very complex at that time. So even if we have not met all the scientific and technical goals that we have set at the beginning, I think that the collected data are extremely valuable and good, and we have already pushed the state of the art a bit further, and the scientific results out of those flights are being published, or they will be very soon. They are under review. Thank you, and I will answer your questions.
Thank you, Gauthier, for your presentation. Anyone have a question? Yeah, I have two questions. The first one is, which kind of autopilots have you used in your UAVs?
The autopilot is, so it's using the Paparazzi UAV system for the software, and for the hardware, it's a custom design, or maybe I missed it. Okay, no, sorry, it's not written. It's a custom design that we have developed at INAC. This board is called Apogee. It's a simple microcontroller-based autopilot. It's very similar to the Pixel autopilots. It's using STM32F4. So everything is running on all the navigation, and the autonomous adaptive navigation is running on the microcontroller.
Okay, thank you, Gauthier. And the second question is, have you implemented an algorithm of synchronization between the two UAVs used in the mission?
Not yet. So there is no direct automatic synchronization, but when we were flying the two UAVs at the same time, so when one of the UAVs found a cloud, we manually sense the second one at the same clouds and at different altitudes, so we can do some kind of layers of clouds. And yeah, one of the future works is to automate this with high-level goals and a task planning system. So you can say, okay, I want to follow a cloud while measuring the airflow. So the system knows that it needs 2 available aircraft, and they can send it to the correct place. So in this example, you have only one tracking, and the second one had to go back before actually reaching the same cloud, because we are only interested by following the same cloud by multiple UAVs, not several clouds apart.
Okay, thank you, Gauthier. I think presenter, thank you, Gauthier. I think the presenter for the paper number 13 is not connected. I didn't find it. Uyuki, do you see him or see her? No. Could you please play the video, Uyuki, in order to maintain the schedule? Thank you.
Hello, good morning, and welcome to a presentation about my research project developing a modular tool to simulate regeneration power potential using orographic wind hovering UAVs, which is quite a title, but we'll break it down for you in a short bit. I'm Vidas Fossi. This is my research project I'm doing to acquire my master's degree, for my thesis project from acquiring my master's degree in aerospace engineering from Delft University of Technology. It's a joint project in the Netherlands drone working group, which I'll explain to you shortly. And also in our group are Sanyu Huang, PhD supervisor, and my supervisor as well, Bart Lemes, also from the MAV lab from the Delft University of Technology. I'm really thrilled for you to be able to show you the progress I made in our project today. So first, a short outline of today's presentation. So first, some general information about the Netherlands drone project, where this project fits into. I'm going to tell you some of the previous research that was important, or sort of that was the stepping stone for our research itself. Some of the research gaps we identified, then the main show our research itself, and then some test results of our test setup of our regen trajectory as well. And at the end, there also will be some time for some questions. So let's get started. So the Netherlands drone project, it's basically a working group where we try to find enough of ways to have a UAV stay in the air indefinitely, ideally through harvesting energy from the environment in some way, shape, or form. Of course, there are already very old methods that you could use, like regular soaring, as you can see in the picture below, with regular sailplane. With this method, of course, one of the issues is that you're really dependent on the current conditions. So either you need a hill close by where you can get ridge lift, and also, of course, a sufficient strong wind that's aligned properly with the ridge itself, or a good thermal. But the problem is, you're really dependent on the conditions. And if, for instance, you want to stay at a certain physical location itself, it's also really difficult while harvesting energy. Another more modern method is to basically use solar panels on the plane. It also has it has the advantage, of course, as long as you have sun, you're able to do that anywhere. It doesn't matter which altitude you're circling at. But of course, as soon as if it's like a really cloudy day, or at night, for instance, you're not able to take advantage of that. It's also really tricky with the charging system involved as well, which brings us to another example. For instance, inductive charging systems. They have the advantage if at every site you install one of them, you can just have, if the power transfer is big enough, you can just have a drone, hovering there indefinitely, and then even also charging the battery while doing another mission at the end when it's fully charged. The problem is you have to install one of these systems at every location you want to charge your drone, as well as that you're you have to have quite quite some infrastructure in place to also support there's high losses basically between those two coils, so you need quite a big power source as well to be able to do this. One novel method that I wanted to research was trying to see if we could combine so-called regen soaring and wind hovering techniques to be able to hover in the updraft of, for example, a hill or another large object like a ship, for instance, and then use regenerative drivetrain to be able to use the excess atmospheric energy in that updraft to recharge the battery while you're still hovering in that same location. But in order for that to happen, I'll first explain some of the two basic concepts that that concept combines, mainly so regen soaring and then later wind hovering. So with regen soaring or regenerative soaring, full out, you use it's pretty much like a standard or sailplane catered electric UAV, for instance, but you're also able to use the propeller as a wind turbine, so not only as a propeller, and your motor as a generator. And what this does is you're able to, if you engage it as a turbine, be able to apply extra drag to capture more atmospheric energy, and then store that energy through, if you have the correct power control unit that is able to reverse the power flow, then you can use that to recharge your battery and store electrical energy. So for regen soaring, you can, for instance, you can just do normal ridge soaring as well, of course, but then instead of storing your energy in the form of potential energy in the form of altitude, you can also first recharge your battery and then still go on to a higher altitude, or even use it to, if you, for instance, for some reason your mission requires you to stay at a certain altitude, you can still harvest energy, otherwise it would be impossible. Now the regen soaring concept is actually already quite old. It was first proposed by Paul McCready, quite a famous name in the soaring world, in 1998. But he mainly just touched upon the possibility of this concept and the techniques required, and technologies also that would need to be further developed. But in 1998, it wasn't really feasible yet with the battery technology available at the time to be able to construct a feasible prototype. Then further research was done more recently by Philip Barnes. He actually designed a concept regenerative soaring plane, as you can see the picture on the right-hand side below. And what really got from his paper was that the trade-offs required for trying to design your drivetrain for both propelling your UAV as well as or sailplane, as well as trying to do the regenerative part, which actually proves to be quite tricky. Unfortunately, he didn't really perform any experiments. It stayed with just a concept plane design. There is, however, one commercial use of this technology already, which is the Mistral Alpha Electro. Mistral is a Slovenian company. It makes this really nice light training aircraft. I think it was actually the first electric aircraft to be certified. And it uses a specially designed wind prop, which is a propeller that they designed to be able to be both efficient in the propelling and the wind turbine regime as well. And it basically uses its special drivetrain to regen aero brake during the descent phase, and it has a special power control unit or PCU that is able to maximize the regen power by having a feedback loop where it monitors the RPM and tries to be in the perfect range where it can harvest the most amount of energy. And they use it mainly because this aircraft is designed to do circuit training. And if they can do steeper descents, and then while in the meantime also recharging battery bits, they can, with the same battery capacity available, they can actually do more training circuits once for the student, which is really beneficial. Then the second concept we need to touch upon is wind hovering. So wind hovering, in contrast to regenerative soaring, wind hovering, you actually try to stay in the same physical location. So you're trying to find a point in an updraft of a wind field where, with the current conditions, and of course, if your UAV is aerodynamic enough, it is able to orient itself in such a way that it can just not climb, not descend, but actually hover in that same location. The main paper that's already explored this concept was emulating avian orographic soaring with a small autonomous glider back in 2015. Actually managed to do some successful hovering experiments in front of a hill, even some very short experiments in a building where they managed to do it for a couple of seconds. They mainly developed the hovering flight dynamics equations that we used as a basis for our calculations as well, and the concept of the feasible soaring region that you can see in the right-hand corner below, where they try to construct a contour region, or visibly see that, where the updrafts are high enough for a certain UAV to be able to, if the conditions are right, that they could hover in that region somewhere, which was what we also used as a basis for our concept. And then finally, the last piece of the puzzle is region electric drivetrains. What's really interesting is there's already been a lot of research into region electric drivetrains, but mainly into light electric vehicles like e-scooters, e-bikes, and even light electric cars. But what's interesting in these lighter vehicles is that they try to optimize their system, where they use the three-phase inverter for both. They try to use it as double duty for both the motoring regime as well as the regeneration regime. So they basically cleverly use these components with a different switching algorithm depending if they want to generate or provide power to the engine, which is of course really good for also using in UAVs, because you have less heavy power components required, which saves mass. And they also even use the coils of the motor itself as part of a boost converter to be able to, if the voltage that is regenerated by the engine is lower than the battery voltage, they use those coils of the engine itself to boost that voltage up to the battery voltage again, so they're able to recharge it. So it's really optimized control system. But even with this research in place, we still identified some research gaps. So as pointed to earlier, most research doesn't really contain a lot of practical experiments. And the whole the wind hovering concept doesn't seem to be explored yet. So the combination of the wind hovering plus a regenerative drivetrain and finding efficiency figures of this optimized regen drivetrain, it's also not really possible. So we set out to our research set out to try to bridge some of these gaps. So our research mainly focused on the two areas, which was trying to estimate the optimal power regen in a certain wind field. And this, of course, sort of entails two subcategories. You need to do first a wind field estimation around the object to see if it's what the wind fields are, to be able to put them through then your flight dynamics equations for your regen system, determine what the estimated power will actually be that you could be able to regen from it. And then secondly is determining the efficiency of the regen electric drivetrain, the optimized regen electric drivetrain, with that combined switching methodology that I pointed to earlier. So first, the estimation of the wind field. There's of course many ways to do it. You can do it with CFD analysis tools, but we opted for actually first doing it relatively simply with a potential flow simulation. The nice benefit of this is that you can easily alter the flow conditions and shape, and then have a very light computational tool that is able to give you results already. So it's very quick and easy to alter the conditions. And also in the back of our minds, we're thinking of trying to maybe implement this algorithm later on board as well on UAVs, which also benefits considerably from having a very low computational footprint. For these potential flow simulations, we also try to include the wind gradient effect. And we did that by using a standard logarithmic boundary layer function that they can use for wind turbines to determine what the wind speed is at a certain height, or determining what also the power would be from wind turbines at certain heights, which proved to be really useful. And on the bottom right corner, you can see an example of the output from our wind field estimation tool for an oval-sized hill. Of course, developing this altered potential flow diagram, flow program would be pretty useless if we didn't try to verify it first. So we did actually perform some calculations with the OpenFOAM CFD package with the simple foam solver. And for some select cases, we actually did simulate it through the CFD package. And the nice thing is we also made our tool compatible. So later our tool is able to calculate the actual power contours. It's also compatible with the outputs from the CFD package. So if you actually take the time to do more complex simulations, like for instance, with around the hull of a ship, you're also able to import that into the tool to see the contours around those shapes as well. Next, the flight dynamics bit. The wind hovering flight dynamics, wind hovering regenerative flight dynamics were based upon that avian soaring paper that I referred to earlier. An important addition, of course, is the drag of the turbine, which wasn't there before. But this drag is, of course, variable depending on how much you sort of activate or how much load you draw from the turbine. We found out that it is you're actually able, if you take the Betz law as a simplification for the maximum amount of power / drag that the turbine would be able to draw from the wind field. You can express this as a sort of a drag coefficient, which you can set equal to 2/9 of the fraction of your disk area of the turbine versus the surface area of the wing. And with that, we were able to construct a very basic hovering criterion. So if the required combined drag coefficient of your clean aircraft plus the part of that your turbine needs to generate, if that is between either the minimum drag, basically, so it's just of the clean aircraft without turbine activated at all, basically folded, the propeller folded back, or the drag coefficient of the clean aircraft plus the turbine at maximum utilization. If that criterion can be achieved, then you can conclude that the UAV can actually hover in these conditions. This is an example of what it looks like if we put it through our tool. So this is an estimation of the regen power region for a 50 meter per second wind field around a hill with a radius of 50 meters. And the more dark red the area is, the higher the power figure. Interesting to see also is the turbine utilization. So we could see that in the previous slide for for example, for these points where, of course, the wind velocity is low, it's very low, even when your turbine is completely, you try to take the max power draw from a turbine because there's not a lot of wind, you get a very low power figure. But more in these regions, you got a higher power figure, and there also you have, so this is sort of the optimum point because you have a relatively high wind speed, and you can have a maximum utilization of your turbine. Then the next thing that we needed to look into is the electric drivetrain efficiency, which turned out to be also quite a hassle because these we couldn't really find out these figures from literature, and we needed to find a way to determine the power available to recharge actually the battery, given your mechanical power that we get from the estimation from our wind field. And this both includes the efficiency of the BLDC as a generator as well as the regen controller. We used a test setup with 2 engines coupled back to back, and for the regenerator controller, we used a commercial VES Hero Desk with a custom STM32 microcontroller that was able to program in a set braking current. This is what it looked like. So we have 2 engines coupled with mechanical shaft coupler. This one, the right-hand engine was driving, the left-hand engine was connected to a torque measuring setup as well. And then the left-hand engine was then connected to the Desk regen controller, which was then able to do the special switching, the switching element algorithm, whereby even if the generated voltage of the motor was lower than the battery voltage, it was able to boost it up using those switching elements. And the motor coils as a boost converter, and then convert that to a higher voltage for the battery. And we basically ran this test setup for quite a couple of parameters. And then we ended up with these nice efficiency graphs. So as you can see, it's really dependent on the RPM and the requested mechanical, the available mechanical power. But we are actually quite pleasantly surprised. We were able to get a top efficiency figure of around 70%, which is actually higher than we first expected. And you can also see the details of our test setup on the left-hand corner. So this concludes basically the research at this point. If there are any questions, please let me know, and I'll be happy to answer them. Thank you for listening.
Thank you, Oyuki, for playing the video. So finally, in order to close this session, we return with Gauthier. Are you ready for your next presentation?
Yes. Just a moment.
Thank you. Go ahead.
Okay, can you see my screen?
Yep, we can see your screen.
Okay, so hello again. So I'm Gauthier Tomberger, a researcher at INAC, the French Civil Aviation University. My presentation here is about the estimation of the wind using quadrotor. So of course, estimating the wind is very useful, and we have just seen that with the previous presentation and others. And in this paper, the idea is to use the motion of the quadrotor to get a proper estimation of the wind. So first, how to measure the winds from UAV. The obvious idea would be to use a direct wind measurement sensor that could be using ultrasound, pressure, or any other techniques. And but in this case, most of the time the sensors, they are either heavy, expensive, fragile, and you can see on the picture below that it can be difficult to or constraining to install them on a small UAV. But usually the main benefit is that they can observe fast variations, and they are suitable to use for turbulence monitoring, for instance. The second option is to use the trajectory itself, and here we have also lots of solutions that exist for fixed wing when using the ground speed while flying in a circle, for instance, or for multicopters, thanks to the relation between the attitude of the frame and the drag that is generated from the airflow. And well, most of the time it needs some assumptions, especially that the flight speed is constant. It's not the only one, but and the result is that the bandwidth of this kind of techniques is usually lower, and you can only estimate the average winds. And in this presentation, we are going to use this relation between attitude and drag to estimate the average wind and to show the calibration procedure that we have set. Okay, so first I will explain the general equations, then the calibration procedure, the estimation filter based on the Kalman filter, and the experimental flights. So first, the formulation, we have two equations. The first one gives the relation between the ground speeds, or the derivative of the position, which is equal to the relative airspeed and the wind speed. And this equation is known as the wind triangle. The second equation is well, the Newton's law of motions, where the product of the mass and acceleration, so the derivative of ground speeds, is equal to the weight, drag, and the sum of weight, drag, and thrust in vectorial form. So we already have some assumptions. Well, we only consider rigid bodies, frame and propellers. The inputs of the system are the thrusts from the motor, and they are all along the vertical body axis. So that's really a traditional quadrotor. And the position and orientation, they are measured or estimated without noticeable bias from the fusion of GPS and IMU data. So the general idea is that in the presence of winds, the thrust of the frame, the quadrotor, has to balance the drag and, well, not the acceleration, but the product of the mass and the acceleration from the previous equation. So here, if you have some winds, it creates some drag, and the frame has to bank towards the winds to equilibrate. So what we need to know is the relation between thrust and the bank angle. And also, if we want to solve this problem, we have to measure the weight, which is quite easy, and to estimate drag and thrust. So the thrust model, here it's the thrust projected on the Earth axis, is estimated to be the total thrust, so the sum of all the thrust generated by the motors, rotated thanks to this rotation matrix, which represents the rotation and the orientation of the frame with respect to the Earth frame. And the drag model, it's usually the drag, the friction drag, is a function of the square of the airspeed, but it's not only that would be true without the motors, but since we are using motors, there is also a rotor drag known as the H force, and which is linear with the airspeed at constant rotor speed. And considering the small airspeeds of the quadrotor, it appears that this linear force is dominant in the drag, and we assume that the drag is again proportional to the norm of the airspeed vector, the A. So we have to estimate for both the total thrust and to estimate or to calibrate total thrust and the drag coefficient K. So the calibration methodology, well, it's simple in principle, but it's not so easy to practice. You need some equipment. The idea is to fly at a fixed position so that we eliminate the acceleration terms. And we fly in front of known winds, and we turn in front of these winds. You will see later why. In this case, again, we know that the projection of the thrust on the vertical axis is equal to the weight, and the projection of the thrust on the horizontal plane is the drag. And we are looking for this relation between the alpha equilibrium, so the buoyant angle, to the drag. So for different wind speeds measured with a reference airspeed sensor, like a hot wire probe, we make at least one full turn, and we record the attitude angle, so phi, theta, and psi angle, and we fit the roll and pitch angles with respect to the heading, so the psi angle, with a sinusoidal shape. And so you will get at least 3 parameters, and we are only interested by C1, which is in fact the magnitude of the sinus, the sinusoidal form, and which is equal to the alpha equilibrium that we are looking for. So before looking at the calibration results, let's see the setup. We have built a custom quadrotor with a spherical body so that it eliminates all the asymmetrical drag, so it's independent of the orientation of the quadcopters. And we fly in a fly area equipped with the OptiTrack system, so the position is automatically controlled by the autopilots, and we have the quite good assumptions about the zero acceleration. And we are also using this wind generator here. This is coming from the WindShape company, and it can be seen as an open jet wind tunnel. And we can, of course, measure the reference speed at the location of the rotorcraft. The system is equipped with the paparazzi autopilots, by the way. So the calibration procedure is to make, as I said, one full turn with a stop of 3 seconds every 20 degrees. We can measure from 0 to 10 meters per second, but we have stopped at around 6. And you can see on this plot here on the right that you can fit a proper sinusoidal shape on the data plots here, plotting the roll angle against the psi angle. And the C1 coefficient here can be extracted from this fit based on the MATLAB function for data fitting. And this is for a given reference speed of 6.57. If you do the same procedure for different airspeed and you report all the C1 coefficient for the different reference speed, considering that at 0 you have a 0 bank angle, you can see here that all the dots are well aligned, and the slope, the coefficient of this line, named C alpha, is related to the drag coefficient that we are looking for by multiplying by the weights. And for our aircraft, we have the drag coefficient of 0.23. Now that we have a calibrated model, we need to build the estimation. And for that, we need some extra assumptions. The first one, as we are looking for the average wind speed, is that the wind is constant or slowly varying. So the derivative of VW is equal to 0, which means that the acceleration, the initial acceleration, is also equal to the acceleration in the airframe. Also, the weight is balanced by the TZ, so the vertical thrust in the airframe, which means, again, that we have no vertical acceleration on the vertical axis. And then we can estimate the total thrust based on the mass and the bank angle. Oops, sorry. The estimation is done using a linear Kalman filter. Since we have this linear expression for the drag, we can use this linear Kalman filter here presented in the discrete form. The state vector is the relative airspeed and the wind speed in the earth axis. The measurement vector is the ground speeds measured by the GPS or the motion capture system. And that's it. And you can eventually neglect the second order terms. So the indoor test that we have done in front of the wind shape system, the wind is constant at 3.8 meters per second here. And it's coming from a fake north, let's say. So here we can see that the wind direction is correctly estimated. So it's towards the P, so 180 degrees, blowing towards the south. And the norm is converging slower, around 20 seconds to get a correct estimate of the norm of the wind speed here at 3.8. We have done also 2 sets of outdoor tests. So we went to the airfields and with 2 different trajectories. One is a square trajectory here at low altitude, and the second one is a vertical profile up to, I don't remember exactly, but okay, so it's a vertical profile. We have looked at the wind conditions on public data websites, and if you compare the time of the flights and the recorded data, we expect to have for the square trajectory wind speeds between 0 and 7, so it's not very accurate. And after 10, between 7.5 and 9. And the direction would be from 110 degrees, more or less. So again, the results, I didn't tell before, but this is the state vector elements, and this is reconstructed the norm and directions of the wind. We can see that the estimation of the direction is, again, fairly good, where we have here the 110 degrees reported in radians. And the norm for the case of the vertical profile, so the vertical, oh, sorry. Here you have the convergence toward the expected wind speed. Also around 20 seconds, a bit less. And you can see that the signal on the state vector here, it's much more noisy than the indoor experiments. And that's due to the noise of the GPS much higher than the motion capture system. Yeah. For the square trajectory, of course, the estimation of the airspeed is much different because we are moving horizontally. So we can see with the large variation that the airspeed is of the frame is estimated, and that's the component of the winds are moving much more than in the previous case. And you can see that here if you reconstruct the direction and the intensity of the wind. Okay, it's less accurate and more noisy than the previous case. So it's probably due to bad compensation of the acceleration, but it still provides some acceptable results. So as a conclusion, I would say that this work summarized the methodology for wind estimation and calibration that you can find in the literature. So most of the elements exist in different forms, different models around the literature. So we put that together to get this initial estimation procedure. And a linear Kalman filter is evaluated for indoor and outdoor flights, and it's providing fairly well results. There are still interesting works to do after that. The first thing is to integrate the codes for onboard estimation. This is actually already done, and I'm just waiting for a technical constraints to push that into the code base of the paparazzi UAV system. So it will be done soon. And also to compare the indoor calibration using complex equipments with outdoor methods, so based on flight test analysis, and also try to integrate some onboard estimations. And also, and finally, test different geometry, different propeller size and rotation speed and so on. And that's it. Thank you.
Thank you, Gautier, for your presentation. I think we have time for one question, Jose. Am I right?
Yes, go ahead, please.
I don't know if someone has a question. Yeah, we have a question. Are there other methods that could be compared with this method you propose?
So the other methods, they mostly ever differ in the model that they use. So the drag model can be nonlinear, and then they need to use extended Kalman filter, or they use slightly different calibration methodology with free flights, with flight data analysis, or using wind tunnel with force and moments measurement systems. So everybody is making some little different solutions. More or less, they all give the same results. What is not very clear, and what I couldn't find, at least in the area of the micro UAVs, is the influence of the body shape. If I remove the ball, the plastic shape in the middle, is it really making a huge impact? And more important, the impact of the motor and propeller size, all of that, the weight of the frame and so on. So probably it exists in the helicopter literature, because the H-force is well known there. But for the micro UAVs and for the drag estimation, it's not very clear, and people tend to use fixed coefficient, and that's it. And yeah, and online estimation integrating into the filter is also considered by some people, but you may have a weak observability of the parameter, so it makes things tricky, and you have to provide accelerated flights and so on.
Okay, thank you, Gautier. I think we have no more questions. Thank you. I think we can continue with the